Hello, everyone. How are we doing today? Great. So my name is Adam, and I head autonomous computing at AWS. I'm joined today here with my friend, Clarissa Reitel from Siemens Energy, and where she's leading efforts around digitalization to help improve the performance and operations of power plants. So today, Clarissa and I will share some benefits of digital twins, and then we will talk about how we're working together to help Siemens Energy and empower Siemens Energy to develop new products and services for their end customers. Now, when we talk about digital twins on AWS, we'll see that it's a very interesting topic to many of our customers and generates a lot of interest. And one challenge we found, however, is that there are many different meanings for digital twins depending on who you talk to. So we always start our conversations by first level setting. So when we think about digital twins at AWS, we really think about digital twin having four key elements. The first part is the physical system itself. And by that, it could be a piece of equipment, it could be an assembly, it could be a biological system, a chemical process, an ecological system, it could even be a human being. The point is, it's something physical and real that exists today. Then there is the digital twin, or the model itself. And in this case, we mean more than just a computer science data model, but really we mean a behavior or response model, one where you're able to provide it an input and it returns back a response output. Now the third element is the connectivity between the two, and this is the data connectivity. This is the key to the digital twin. And really what's happening is the real-world operational data is coming from the physical system and updating the model itself. And this is important if you want to be able to use that model to make predictions of the future and for what-if scenario analysis. The fourth element is really around business outcomes. Really, every digital twin has a purpose. There's a reason why it was built. And this is really important because we will always work backward from that desired outcome in order to understand key things such as what part of the physical system do we need to model? And what is the level of fidelity or granularity of that model that we need to build? And then how often do we need to update that model from the real-world operational data? All of those things are very, very dependent on the specific use case that you're trying to achieve. Now, when we talked with our customers, we found that we really needed to expand our interpretation of this in order to be able to consider use cases that are alternate to these that our customers consider as digital twins. And in doing so, we took inspiration from the automotive industry, where they have the autonomous vehicles have a 6-level system. They have level 0, which is a human being driving a car, so not autonomous at all. Level 1, which is sort of 1980s style cruise control. Level 2, which is adaptive cruise, all the way up to level 5, which is really an autonomous vehicle where there is no steering wheel, just get in the car, tell it where to go. So we've done something similar. We've proposed a 4-level system, where level 4 is consistent with the definition I provided earlier. And level 1 through level 3 is really representing different categorizations of use cases that are driving business value today for our customers and our customers are asking for. Now we have here a blog that provides a lot of the details. There's a QR code in the URL. I'll go through it really quickly today just to give us some context. Now the first level is descriptive, and here the purpose is to really describe the structure of the system. And this includes all the engineering analysis, the scientific simulations, any kind of 3D virtual representation, such as a virtual walkthrough. That is all level 1. And this would include, for example, high performance calculations, computational fluid dynamics, finite element analysis, or 3D virtual reality training, or imagine you're an architect and you have a new house that you're building and you have a virtual reality walkthrough for your client. They can see their house before it's built. That would all be level 1. Level 2 is around understanding the state of the system. And this is through the data connectivity. So use cases such as single panes of glass or data dashboards, those are all level 2. Now we see that we're seeing customers use more and more 3D visualizations. So more complex visualizations, such as imagine you have 3D VR glasses and you're able to do a virtual walkthrough of your factory floor. And while doing that, you can point to different pieces of equipment, click on that equipment, and pull up the sensor data for that equipment, all virtually. that would also be a level 2. Another use case would be the augmented reality worker assist. In that situation, you might have a technician who's actually working on a part. They're out on the shop floor, and they're using augmented reality glasses, or they might have a tablet, and they're able to put that up, and they're able to get an overlay of relevant engineering data, for example, say the engineering drawings or the service history. That's also another level 2 use case. Level 3 is about predicting the behavior of the system using a trained model. So the implicit assumption here is that future behavior is predicted well based on past behavior. And the type of use cases you could use there are virtual sensors and anomaly detection. Level 4 is also around predicting the behavior of the system, but in this case, future behavior is not necessarily based on past behavior. So this can happen when you have situations where the physical system is evolving in time. Very commonly, you could see equipment degrading. So for example, a gas turbine engine that's brand new behaves quite differently than a 20-year-old gas turbine engine. So in that case, you need to be able to update the model itself to truly reflect the behavior of the system. And this is very important to be able to, once again, make predictions of the future and do what-if scenario analysis. Now, I'm not going to go through this in detail. You can see on purple, I'm sort of flashing up a range of AWS services that we have for each one of the levels. And there are more as well. I'm not going to go through that in detail, but I will highlight 3 of the services and solutions that we have that are relevant for today's talk. The first one is focused around level 2. And this is one of our newest services. It's called AWS IoT TwinMaker. And it really, as the name implies, is there to help customers and partners build digital twins. In itself, it is not a digital twin by itself. And it does this by addressing 3 main pain points. The first is to connect disparate data from different data sources. So in this particular case, the philosophy is not necessarily to copy the data to a central repository, but rather allow the data to live where it naturally wants to reside and build connectors out to those data sources. And then there's a semantic layer on top of that and a knowledge graph on top of that, and that allows the customer to be able to then query the data whenever it's needed. The second is the ability to maintain the data model as the asset evolves over time. Now, we've heard from our customers how it's really a lot of work to actually get the initial configuration of the equipment correct. Just knowing all the right serial numbers and parts, getting that up and put into the database is a lot of work. What's even more work is keeping that up to date as maintenance activities occur, repairs occur, and parts are replaced. So we've made that easy through this service through a relevant set of APIs. Lastly, we're addressing the ability to make effective visualizations as easy as possible. I mentioned earlier the world is moving more and more towards 3D visualizations. So IoT TwinMaker makes it easy to build 3D scenes from any kind of 3D format, or a wide variety of 3D formats, and then be able to create data tags and associate sensor data and other types of data to those data tags and different objects in the field or in the scene. So that gets us to that 3D contextual awareness type situation. Now, the next service is really around level 3. Here we have a host of services for industrial use cases. And what I'd like to draw your attention to is Amazon Lookout for Equipment. This particular service is really around anomaly detection for industrial equipment. It takes sensor data, it monitors it, and analyzes it, and looks for anomalous behaviors that could be precursors to failure. And you can do this without being a machine learning expert on your end. And this, later on, we'll hear from Clarissa as she'll describe how Siemens Energy is using Lookout for Equipment to predict anomalous behaviors in the heat recovery steam generator in a power plant. The last one I'd like to talk about is around level 4, and this is something relatively new. Level 4 is really at the intersection of 4 main areas. The first is around having deep domain expertise. So this is first principles knowledge. It could be physics, biology, whatever the particular science is. Machine learning, deep learning, and most importantly, probabilistic modeling. This last bit is probably the add-on that's relatively new. This probabilistic modeling, usually it's Bayesian inference methods. These are necessary in order to update the model parameters as the system evolves over time. This is key because this is what makes the digital twin living. Now, to help our customers with this, we realized that these methods are out there today. They're in academia, and they are in R&D labs globally. But they're certainly not readily available to the masses. So one of the goals at AWS, in fact, one of my personal goals, is to democratize the techniques. Make these techniques available to all of our customers so that any of our customers can, I'll say, relatively easily make a level 4 digital twin for their particular use case. So to do this, we've open sourced the AWS DoPM framework. I've provided a QR code and the URL to the GitHub repository. And PM here stands for predictive modeling. This allows our customers to take their models and wrap them with the necessary Bayesian inference techniques and methods so that it can do the model update and model calibration. Later on, we'll hear from Clarissa, who will describe how Siemens Energy is using these techniques and methods to predict corrosion, once again, in the heat recovery steam generator of a power plant. Now, before I do hand it off to Clarissa, I will dive a little bit deeper into the workflow for a level 4 digital twin. It really has 2 phases. The first phase is around model building and initial calibration. So you have a training data set of some kind, and you build your model. This model could be any type of model. It could be a physics-based model or a first principles model. It could be a ML, machine learning model, like a neural network. Or what we're seeing more and more are hybrid models, such as physics-inspired neural networks and other hybrid techniques. You then do a sensitivity analysis on this model to understand what are the key parameters of the model that have the largest impact on the output. And once you understand those model parameters are the ones that we will be calibrating against as we get real-world data coming in. So then we'll perform an initial calibration using, once again, these Bayesian or probabilistic methods and techniques to calibrate those parameters. Then, once that model is calibrated, we move to the second stage, and we move the model into production. At that point, the model is deployed, and it's used to make a prediction of a particular sensor or a particular value that you'll get from the real-world system. Then as operational data comes in, we then take that measurement and calculate the difference, basically calculate the error. And if that error is below a threshold, then nothing happens, the model is fine, and you just kind of continue until the next model sort of prediction is done. If the error is above the threshold, then we trigger that same probabilistic method and calibration technique to update the model parameters. And this is done to reflect the operational data. This is the key part that keeps the model live and truly representing the behavior of the actual physical system as it evolves over time. So now I've covered a lot of ground here today, really just to provide some context. Now we'll have a chance to learn about digital twins in action from Clarissa. She'll share with us how Siemens Energy is applying level 3 and level 4 digital twins to improve the power plant operations for their end customers. Clarissa, I'd like to invite you up. Thank you, Clarissa.
Perfect.
Very nice
Thanks,
seeing you
Adam.
again. Here you go.
Perfect. Let me just quickly open my water. So, hello everyone, and also a warm welcome from my side. My name is Clarissa, and I'm heading the strategy team for our service business at Siemens Energy. Today, as mentioned by Adam, I would really like to firstly introduce Siemens Energy quickly to you. Secondly, talk about our vision for digital twins. And thirdly, show you how we put it in practice jointly with AWS. Before I start, maybe just a quick question for me to calibrate. Who of you guys knows Siemens Energy? Can you maybe raise your hands? Oh, okay, good. It's a good 50%. That's cool. And for the rest of you guys, buckle up. We will get into some really deep data of energy and of power plants. Talking a bit about Siemens Energy. Siemens Energy is dedicated to oil and gas, power generation, renewables, and transmission, where we deliver our core components, like steam turbines, gas turbines, or compressors, ranging from products to systems to whole power plants. But we, of course, don't stop there. I mean, you have heard it. I'm the head of service strategy. So, of course, we also are very proud that we service all these equipments and help our customers even operate them. This also makes us, as Siemens Energy, basically the one company in the world that services the entire value chain of energy, which gives us, which makes us very proud. But at the same time, it puts us in a sweet spot that we can really shape the future energy world. And talking about the future energy world, I think it's really clear. With our standard gas and steam turbines, we will not make it. I mean, we are committed, and we really also want to commit and help decarbonize the world. That's also why we work on other things. We have renewables in our portfolio, and we also offer systems for hydrogen or other green energy carriers. At the same time, we understand that it's not only products. Digitalization is one key driver for the future of the energy world and for making energy greener. This is why we also in Siemens Energy said that digitalization and working on digital twins is one of our 5 fields of action, and I am very proud to also head this field of action, and that's why I'm currently working together with Adam. At the same time, we also reflected and we said, hey, we are an energy company. We are not like AWS. We are not a digitalization company. So let's be wise, and let's use all the intelligence we have in-house. Let's use our own OEM knowledge, but combine it with what's out there in order to also be quick, because if one thing is pretty sure, the energy transition is coming rapidly. We need to support our customers, and we cannot wait. So, as said, we were looking for partners that help us jointly drive the energy transition. And we found them. We found them in AWS and NVIDIA. If you look at AWS, 90% of the workload that we have in Siemens Energy is currently already running on AWS services. So I don't need to tell you guys what AWS all does in terms of services, scalability, and operations. But what really impressed me over the course of the last year, and also since I'm working closely together with Adam, is the AWS track on machine learning, which really helps us bring our digital twins forward. And NVIDIA is plainly the deep learning company in the world. And we are very proud to have them on board because they help us with their GPUs, with their edge cloud knowledge, really driving things forward. So these 3 parties that you see on the slide also signed a memorandum of understanding last year, where we committed that we really want to shape the digital twins in the energy world to, first of all, increase safety of operations for our customers. Secondly, increase the efficiency of power plants, resulting in higher capacity, but also then reducing emissions. We want to reduce costs. We want to optimize the utilization of the plants, and all that while supporting the transition to decarbonize our energy supply. So let's talk a bit more about digital twins and our vision for digital twins that you can see on the slide. For us, digital twins are a good way to combine our Siemens Energy heritage on really deep, different analytical models and combine them with machine learning and deep learning technology. And we are convinced we need all 4 of them to really make a change. How did we come up with these 4 digital twins? We basically talked a lot to our customers, we talked to the market, we talked to analysts, and in the end we found these 4 digital twins are really addressing the pain points of our customers and will help drive the energy transition. So let me maybe quickly guide you through them. First of all, the energy management twin. The energy management twin is really around when you want to operate a decarbonized energy system. So a system where you don't only have classic gas and steam turbines, but where you have renewables in. Renewables, I mean, we all agree, will help shape the future, but at the same time, power from renewables is volatile. So when you have one of these systems, you always need to be prepared and need to know how much power do I have in my system, how much power do I currently need for my operations, and what do I do with the gap? And that gap can be 2-sided. Either you have to less energy. Well, what can you do? You can buy energy from the grid, but then it's maybe not decarbonized, nothing that you maybe want for your operations. Or at the same time, you can, of course, think about storage. At the same time, what you can also find is that you have a surplus of energy. The wind turbines are running, the sun is shining, solar is up. What you need to do then is, of course, you again need to think, do I store this energy to use it later? Or do I provide it to the net and do I dispatch it? So this is one main focus where we currently work on to basically help our customers find these perfect operations points and also optimize then in the end the performance of the microgrid, which will help our customers increase their revenues and lower their costs. The second twin we work on is the energy consumption twin. The energy consumption twin, we basically came up with that because we found studies that say, hey, when you look at energy-intensive industries, when you look at fiber, when you look at minerals, where also our core components are deployed, there's over 10% of energy that you can still save in these operations. Saving these 10%, of course, means we reduce the fuel that's being used, we reduce emission, and we at least help to decarbonize these equipments that we find in the market. Thirdly, autonomous operations. Autonomous operations is really about unmanning and demanning power plants. Why is that important? It's maybe not important when you think about a plant that sits here right in Las Vegas, but it gets more and more important when you think about power plants that are maybe in politically unstable areas, when you think about oil and gas applications that sit in the middle of the sea. So everywhere where it's hard to ship experienced experts, we really need to help our customers to un- and demand these plants in order to help increase their revenue, but also, of course, reduce risks and reduce costs. And lastly, the system reliability twin. The system reliability twin is closest to our heart, as I always say. Why? Because there we really look into predicting when is the system gonna fail. And what does it mean for us? When do we need to do service? When do we need to, what do we need to do to maintain the power plant? But it's not only around our core components, and that's what we also will see later. A system reliability twin also looks at like all the little equipment pieces that you find around in a power plant. To just give you an idea, there's over 5,000 equipment types that we find in each power plant, and we of course need to make sure to monitor them in order to increase the probability of us knowing what's going to happen in order to improve our services for our customers. That sounds all nice and shiny, but of course, it's not always going how we want, and there's always challenges that we also see. And let me maybe just honestly also address some challenges that we are currently facing, because most probably that's similar wherever you guys work. So first of all, one problem that we have is the lack of data. So what you can see on that slide is the hydrogen power plant. We are very proud of it. It's one of our newest products. We deployed it. It's running at a customer site. And of course, we want to offer a digital twin, because when you think back around my talk around the energy management twin, we of course want to help include this hydrogen plant into the whole energy net. But at the same time, we are lacking data. And this is bad because, of course, when I don't have data, I cannot predict what's going to happen. When you think about what Adam told you guys earlier, without data, I don't know when something is good and I don't know when something is bad, so I can also not predict anything for the customer. The second problem is speed of simulation. Siemens Energy is really great in simulating through first principle models. We have a lot of them at hand. We have great experts in-house. At the same time, it takes hours, up to days, sometimes weeks, to really deploy these models and process them. What does this mean? Of course, if we are in the design process, or also when we want to deploy these models at our customer side, it takes way too long, and we really need to see how we can speed the simulation up. Talking about the right-hand side of the slide, and I think I mentioned it earlier. When you look at power plants, of course, it's interesting to understand how one of the equipment types work, how a gas turbine works, how a steam turbine works. But the beauty really is when we start understanding the whole power plant, when we start understanding the whole system. In order to do so, we also, of course, have two issues that we are currently tackling. The first issue is the whole question around scaling. How do we scale such a system-to-system approach? How do we make it really efficient? And the second question is, of course, around standardization. Each plant is very specific by itself. And we, of course, need to react to it, and we need to offer our customers a digital twin that works for its specific plant. But nevertheless, what we also want to avoid is massive customization efforts. So there is a balance that we just need to live and work in. Good. Before I now start talking about the system reliability digital twin in detail, I just want to take you on a quick lesson. I'm a strategy person of how Siemens Energy makes money with service, because that's really important for you guys to understand the system reliability twin afterwards. So let's talk about long-term service programs, in short, LTPs. LTPs are one major revenue source for our service business. The service business at Siemens Energy, just to put it in perspective, is roughly 40% of our revenue, but that's not the important piece. The important piece is that it contributes mostly all of our profit. And having that in mind, it's of course A, important to protect it, and it's of course B, really important to not mess it up. If we mess with our service business, the whole company is at stake. And that's also why we of course started and looked into how can we help make our LTPs better. LTPs, generally, we sign them for all equipment types that we sell. And what you can see on that slide here is the example of a gas turbine LTP, which basically gets signed once we sell the contract and then renegotiated after 12 years, which basically means that we as Siemens Energy take the full responsibility of this power plant for a fixed price for 12 years. And we can do nothing about it. We can help our customers, we can improve, but there is one price we get, and whatever happens with the turbine, we need to take care of. Over the course of the lifetime, and that's also what you see on that slide, we of course need to do regular inspections. These inspections ranges from like 1 or day short inspections up to us going into the power plant, deconstructing the whole gas turbine, building it, refurbishing it, and building it back together so it can take up to 2 to 3 months. So for us, it's of course really important to understand, do we really need to go in? What do we need to change? And when do we need to change it? Because of course, as long as the turbine runs, our customers make money, but also we as Siemens Energy make money. Now you may ask yourself, yeah, well, why do you even need to service it so much? And that's where the whole question around gas turbines comes in. So a gas turbine is basically like a jet engine. You can compare it. It's even gas turbines that are being derived from from the aviation industry. And gas turbines, they operate at temperature levels of roughly 1,800 degrees Fahrenheit. So basically there is massive temperature stress that daily runs on that turbine. What does that tell us? That of course tells us we really need to service it in order to be able to really increase the availability of the plant. Just to give you one little impression, when you have a gas turbine, and just as I said, think of a jet engine, you have 400 blades in it. You might say, hey, well, it's not so bad when like in one of the blades you have a little chip when something cracks. Yes, it is. When we have a chip in one of our blades, one of these 400 blades, it basically goes down the whole combustion path and it shreds the whole turbine. And you have $1 million turbine that's just done, that you cannot do anything anymore. You need to take it out and you need to put a new turbine in, which of course would put massive costs on our side. And that also explains, of course, why customers tend to sell in LTPs. You can say, hey, it's nice for you, Siemens Energy, you bind your customers for 12 years, why should they do it? It's pretty easy. For them, it's like an insurance. They hand their risks over to us, and we need to make sure that everything runs smoothly. And this is then, of course, also where digital twins come in place. When I have the possibility to help my service business, to help my field service, to understand better when something is going to break, what we need to do, when I can prevent these little chips from breaking, when I can prevent the turbine to shred, there is massive revenue potential and, of course, also profit potential on our side for Siemens Energy. But at the same time, of course, we are helping our customers because the most interest of the customer is having the turbines run. Good. Let's now look deeper into a combined cycle power plant. And you might wonder, okay, combined cycle power plant, what is this now? I think we already talked about a gas turbine. A combined cycle power plant is basically nothing. Then you have a gas turbine and you have a steam turbine, and both produce energy. Why would you need that? It's pretty simple. If you only have a gas turbine, you have roughly an efficiency of 30%. If you have a gas turbine and a steam turbine, you get an energy efficiency of around 55% of the power plant. So basically you double it, talking again about decarbonization, making the world greener. We appreciate it's still not green, but it's better than before. So that's also, of course, why we sell these combined cycle power plants. What happens in the middle, there sits this famous heat recovery steam generator that Adam mentioned earlier. Basically what this equipment type does is it takes the exhaust heat of the gas turbine, enriches it with water, and therefore basically produces the steam that we later on fire through the steam turbine. So basically it's the middleman in the gas turbine, and of course afterwards that you can see in the end, we use the transformers to put the energy in the grid. So let's look at the heat recovery steam generator. A HRSG, when you look at it, it looks nice, but it's basically a monster. It's really high engineering. It has basically thousands and thousands of tubes that run through this building, and the building is high. It's around a 12-floor building, so you have like roughly 30 meters in height that this HRSG consists. And believe me, you don't want to be around when one of these over 1,000 tubes break. But it happens. And the simple reason why it happens is corrosion. You know it from home. When you have water in a pipe, the metal corrodes, the pipe breaks. You know it when you have an ice cube in a glass, you put hot water over it, it cracks. Nothing else happens in a HRSG, but of course much slower. But if it happens, we run in real problems together with our customers, because firstly, of course, you don't have a HRSG building sitting around that you can just put in and replace. And secondly, the costs are immense. It's roughly 160,000 US dollars for the operator. That's also why, of course, these walls and tubes of the HRSG are being inspected on a yearly basis. And as you know, corrosion builds up. So of course, in the first year, you have light inspections, and year over year over year, the inspection gets more intense because people just expect that at one point something will corrode, there will be a problem. Which means that also year over year over year, the inspection time increases, which also means that the production time, the actual uptime of a power plant reduces, which is necessary because we, of course, want to avoid that something fails, but at the same time, of course, giving high costs for our customers. And that's also why our customers reached out to us and said, hey, isn't there anything that you guys can do? Can you not help us? Can you not predict us? Where is the corrosion? When do we really need to make an inspection? How can you guys help us reduce the inspection days? And we looked at this and we said, okay, I mean, what do we know? First of all, we have a rich experience in HRSGs. We have built over 600 HRSGs ourselves as a company, and at the same time, we operate dozens of power plants, not only of our own HRSGs, but also of HRSGs from other vendors in the market. So we have really a broad knowledge on that. What we did is we brought our experts together from service, from operations, from maintenance, our engineers, and we looked at it and we said, do we really know enough around the physics that we can really determine what to do here? And in the end, we said, yes. We found two things. First of all, what we can identify is the whole question around where will cracks really happen? So where in this huge HRSG do we really need to look? Where do we need to focus our inspections? And then, of course, the second question around, can we really predict when a crack is going to happen? So when do we really need to do the inspection, but also when do we need to do the outage in order to maintain the HRSG? We looked at it, and what we found is that when you look at it in a 10-year period, by doing so, we can reduce the inspection time by 65%, which is a nice number, but at the same time, it will help our customers to basically have the production up and running for a longer time, which will give our customers a benefit of roughly $6 million US over the course of the 10 years. So what did we now do? Let's maybe just quickly reflect on what you heard from me before. what do we really need to look at when we want to determine a digital twin for a HRSG? There's basically 3 factors. First of all, it's the geometry of the tubes that influences the fluid dynamics, and is a typical CFD problem. Secondly, it's the temperature and the pressure that you have, and the dew point of water in the tubes. And thirdly, it's of course the whole question around water chemistry. What kind of water do I have? Different water types let metal corrode differently. Considering this, we in the end designed a 3-step process. First, we needed to convert the paper model. Yes, when you look and when you go and when you find models of an HRSG, they are never in 3D, they are paper. We need to convert that to a 3D model in order to consider the geometry and fluid dynamics. Secondly, we need to find data points for pressure, temperature, and mass flow at the tubes. We don't have them, so we need to simulate them through physical models. This together will be then, with the 3D model, will then be the input for our CFD model to really locate the risk of corrosion. And also, in the end, helps us to set our database up. By knowing this, we can somehow, when you think back of Adam's talk, we are like at level 1, right? We have a descriptive twin, we know what's currently going on in HRSG. But that, of course, doesn't help us. We want to look at the operational data. So we also needed to look at step 3, where we basically map the operational data from the few sensors that we have in the plant to the base cells and really aggregated the corrosion factors. When we then apply actual water chemistry of the water that runs through the plant, we can come up with the real material degradation and get a feeling of how close we are to like cracks or breakdowns of the whole HRSG. What has that all to do with what Adam has told you before? And basically the results of what I will tell you, you can also see on the left-hand side of the slide. And I always say it looks so cute, but it was really a deal breaker for us. So we said we are now at level 1, level 2 of the predictive twin, but we really want to level it up. We want to come up to level 3, level 4 of our twins. In order to do so, we worked together with AWS, and Adam has presented you the AWS DOPM tools, where AWS helped us to create probabilistic models. And you can see it on the slide. What we basically found is we could define the material loss through the corrosion, as well as the location of the pipe. So where is it basically going to corrode? But this was not enough for us. We also wanted to deploy really the predictive models at scale and update the model parameters using Bayesian inference. Why did we want to do this? Because in the end, of course, the question is not only what is going to happen now, but also a prediction when is something going to break. And when we do so, we could also narrow down this whole expectation of when is something going to fail. Because, of course, it's really different when you know that something is going to fail in 6 months plus minus a week, compared to when you know that something is going to fail in 6 months plus minus 5 months, which basically tells you nothing and which was the accuracy that we had before. By this, we were also able to extend our service intervals and therefore, of course, ensured that our customers' production time increased and hence their revenue. Secondly, of course, we ensured that we reached the availability level of the HRSG that we promised to our customers beforehand. And thirdly, of course, also we could improve our own preparedness for inspections. So before deploying our service engineers to the field, we could really tell them, where do you need to look at, where do you need to focus, and what do you need to do? We are really proud that Adam and AWS also chose us as a use case there. And as I said, it looks so small, but for us, this was really a game changer in the whole question around how do we work with an HRSG, how do we predict corrosion? Which also brings us to what comes next here. What you see on the picture are our existing service contracts. And of course, what we will do is we will deploy the HRSG corrosion twin to all of them. But of course, we don't want to stop there. We want to extend to customers that maybe don't have a service contract with us. And at the same time, we of course also want to go beyond corrosion. We want to explore new fields jointly together with AWS. That was the first use case that I brought you. And Adam helped me very nicely because I don't know if you saw it, but he mentioned 2 tools earlier, or basically 3 tools, but let me maybe talk about the second one that he mentioned to you guys, Lookout for Equipment. This is another way how we really work together to create benefits for our customers. So when you look, again, we are back at our gas-fired power plant that I mentioned to you guys earlier. This gas-fired power plant has around 5,000 pieces of equipment, like valves, pumps, you have motors, and all this somehow impacts the power production when one of them fails. We basically have the data from the system. So when you look at modern process control systems, they give us all the data from all these 5,000 equipment types. We looked into it per day. We roughly get 25 million data points from like 30,000 sensors. So we have the data at hand. We know everything. And now you might ask me, yeah, okay, you have the data. You know it. Why don't you do anything with the data? And the answer is pretty simple. It's simply not, we were simply not able to do so because it was too expensive, because of 2 reasons. A, the effort to parameterize the physics models was too high for us. And secondly, when you really want to apply machine learning, you need to not only machine learning experts, but you also need data scientists, and you need subject matter experts. And you really need to take time and put these guys on a table. Talking about 5,000 different equipment types in a power plant, it was too much. We were not able to handle it. But, as Anna mentioned to you earlier, since around a year, AWS offers unsupervised learning service Lookout for Equipment. So now what can happen is simply a process engineer can work with Lookout for Equipment, can assign the different sensor types, can basically name them in the system, run tests, and once in operations, the process engineer can detect the problems and the failures itself. And then, of course, once a failure hits, we can give it to our engineering experts, and they can help us to understand what's really the problem and to feed that back into the system. Let me show you one example of that. So what you basically see on that slide is a dashboard where we first implemented unsupervised learning at one of our customers, GSEPS. It's a Korean customer that basically has several power plants around Korea. And what you can see here is basically a deep dive into the dashboard from the customer from a feed water pump. And again, it doesn't look maybe so fascinating, but it was really, really great for us and was really great for the customer. So basically what we did, we just deployed Lookout for Equipment. We collected the sensor data. Lookout for Equipment showed basically, and that's what you see in the middle part, which sensors showed abnormal behavior within the power plant. We identified it's the feed water pump, and our customer who had problems with that feed water pump, but it didn't even know about it, could fix the problem immediately. So it was really a great success, and it was so easy for us to implement. So I think we had the system running for like 1 month, and then we found all this. So what do we do with that? Let me come maybe back to the picture that I showed you in the beginning of my presentation. Basically, the thing we talked about is the little power generation part in the beginning where I told you we have 5,000 equipment types. So now you look at the whole energy landscape that we put out there. And you can imagine if it's only 5,000 or if it's 5,000 equipment types in a power generation plant, how many more we have in our whole energy system that we service as Siemens Energy. And that's where we want to go, that's where we want to tackle, and that's where we really want to apply Lookout for Equipment, not only for our service business, but also for our customers. And that's, of course, also where we currently work with our operations and maintenance team to identify exactly the right areas to go in. So all in all, what do we want to do as Siemens Energy? First of all, of course, we want to intensify the work with AWS. We want to continue the collaboration on the 2 topics that you have seen before, the corrosion model and also the Lookout for Equipment model. But of course, we want to transfer the learnings further out. We want to look at what other failure modes do we have. We want to also look how can we improve the twins for our core equipment as well as the auxiliary equipment. And in the end, thirdly, and I think I didn't touch on it there, what we also do jointly together with AWS is we use a lot of AWS methodology on how to drive software development, how to really push things out. And that's, of course, also where we want to continue together working with Adam and team. Super. And with that, I come to the end of the presentation and would like to invite Adam back to me on stage because we would have 15 minutes roughly for questions. And of course, would like to thank you guys so far for listening in.
Nice job. Thank you, Clarissa, for sharing your insights on how Siemens Energy is working with AWS. We have time for some questions. Any questions out there? If you do, please just stand up. Yes, sir.
Yes, with regards to the example you spoke about, identifying anomalies, going into this whole product as you design, is it using empirical numbers or do you have some specific bandwidths for your anomaly anchoring?
So what we usually do is, of course, you have the systems running, right? So you have a bit of comparison also when you have multiple of these equipment types, what is a normal way of basically data that should come out. And what we then do is, of course, we give limits, right? We say, hey, if something is like 1 or 2% off, and of course it depends and differs by equipment type, then if we see really this difference, that's when the system's basically gonna alert, that's when the sensor is showing up. Of course, what we also find, and I didn't show it here, is that sometimes we look out for equipment that says, hey, there is a failure, and it's none, right? So there's also a bit of a training and a bit of a learning that we, of course, need to put in. But generally, that's how we do it.
So it's just provided as inputs to your digital twin model, or do you use some kind of a machine learning to even optimize your bandwidth, or like the low end?
So it's basically also then machine learning and also our experts, of course, that we use to optimize, right? Because then in the end, you also, again, feed that back in. You have the artificial intelligence working with it, running over it. And of course, what we also want to do is, and I didn't show it today, I mean, the first thing is to detect a failure and to say, hey, there is a problem. But what, of course, needs to happen then is that our experts sit there and say, hey, okay, this is the feed water pump. Most probably it's A, B, and C. And this is what we need to do. But of course, the next step that we want to go is take exactly this learning. So this is a failure, and this is what we need to do and feed that back in. Because then, of course, our hopes are that next time when the sensor falls out, that we get the feedback, hey, something is wrong, and most probably that's the problem, and that's how you need to fix it. So that would be basically also be the next step of our vision, how to continue working there.
That's helpful. Thank you.
Great. Any other questions? Yes, sir, over there.
Hi, Clarissa. The decision to choose the other pieces of equipment that you're going to go for next, you said you're working with the operations.
Yes.
Can you tell us some of the factors that are going into how you were ranking those?
Yeah.
Sure.
So I mean,
Clarissa, do you want us to repeat the question?
Of course.
Sure. So the question was, as Siemens Energy is looking to expand the use of these methods and techniques, what's the process or the sort of the decision-making, the thinking behind the decisions as to which pieces of equipment they will start with and prioritize? Is that correct, sir?
And basically how we do is we, of course, know what are basically, so it's basically impact and effort, right? So we basically look at all our equipment types and say, hey, what of them, if something is going to break, really has a bad impact on us? And how probable is it that this is going to happen? So it's basically a bit like a risk analysis that we do, combined then also, of course, with the whole question around where do we have enough data and where do we also have the experts that can basically stick around when we implement it. Because the one thing is, of course, to have Adam and co. and to bring machine learning and to bring the tools in. But then, of course, at the same time, we need the subject matter experts that say, yeah, and this is really a problem. This is our expertise. This is how we can handle it. So it's a bit the, of course, effect. So like basically the business case behind the twin, but also the availability of experts. That's how we rank it.
Yes, sir.
Hey, first, can you talk about the services that you use to build this? I mean, is there a site-wise in here? Do you just look out for equipment? What's the entire architectural landscape look like? Because we're traveling down a site-wise path, and this interconnectivity between site-wise digital twins and the entire IoT suite seems to be really important as you go down. So I've been really curious to see what an architecture diagram looks like and the flow of data through services.
So the question for Clarissa is, what does the overall architecture look like for the IoT data that's coming through, and what types of services are being used in that workflow.
Yeah. And to be honest, that's something that we are also currently working on. So we started and we had like little pockets of excellence, and you saw it with the 4 digital twins where we started working on. But at the same time, we didn't have a reference architecture for the last a year, roughly. Yeah. And what we now did is that we also, together with AWS, we set up a work stream that's called reference architecture to actually answer exactly your points. Because honestly, we are also just going down that path. What we have done is we have now set up a reference architecture, how we want to see it. But of course, then the whole question is around, and I think it's most probably similar in your company. For us, digitalization was always driven in little pockets of excellence, which is great, but which hinders standardization. Now, since a year, my program is there. But then, of course, we now need to say, A, what is, of course, the reference architecture, but also how do we bring these other like little pockets and islands along? Because, of course, I don't want to destroy what they have done. And I, of course, also don't want to create huge efforts for them. So that's something that we're also currently trying to figure out jointly with AWS.
Right, for me, I look at the suite, the IoT suite, Twin Maker, what we make, all the stuff that's coming out. And it seems like we're playing catch up. You know, there's pieces here, pieces there, and how do you pick the right path to make sure that you're in line with the technology advancement that AWS is putting together, but also keeps me moving in a path forward that I can begin to provide level 1, level 2 capabilities to my business as I work towards level 4.
Yeah.
Yeah, so we can maybe have a conversation afterwards. I can certainly help you with that. But definitely, if you look at some of our digital twin reference architectures, and we have some of it's actually being published in some of those blogs that I referenced earlier. You'll see some of the blueprints in the reference architectures that we're using. For digital twins, if you're connecting IoT data, we generally use IoT site-wise, IoT core, and we're using lambdas as well for serverless architectures. And the reference architecture you can see that there. For some of the use cases, for example, in another talk we'll be talking about an automotive use case. We're also using FleetWise, which is a similar service to IoT SiteWise, except really geared towards fleets and for vehicles, where it takes in the sensor data from connected vehicles and is able to make that available. Then, depending on the type of digital twin that you're building, you might have connectors to services such as Lookout for Equipment, for in this particular case. Or if you have, say, a custom model that you built in SageMaker, you would then use an endpoint and connect to SageMaker to run that model and then get the data back into, say, SiteWise, and then ultimately that gets pushed into TwinMaker. Everything here that we've shown is done through the TwinMaker service, and then TwinMaker allows us to connect the different visualizations, create the dashboards, and bring in the IoT data. So there's a number of blogs that will show some of this information, but also if you want, my address is there, just email me and we can talk afterwards. I'll put you in touch with a solutions architect who can help you. I think we have time for 1 or 2 more questions, actually. Yes, Enno.
First, thank you very much for the excellent talk, much enjoyed it. I have a question that's very closely related to your question regarding the ranking. When you build a digital twin, you can choose what level of detail and fidelity you want.
Mm-hmm.
I find it very challenging sometimes to decide regarding business value, so what level of detail you need to achieve a certain business value. Do you have established procedures or kind of an approach that you usually pursue when you make such decisions?
So the question is, when trying to develop or decide around the business case for a digital twin, how do you decide, or do you have any procedures or guidelines in determining the level of fidelity that's required for the digital twin to generate the desired ROI? Because if you invest too much into the digital twin and it's very, very expensive and complex, then maybe that eats into the ROI a little bit. So any guidelines or thoughts on that level of fidelity?
And I mean, I think it's a very good question because we discuss that, of course, a lot, right? Because I mean, you can look at it from 2 angles. You can look at it from like basically the level of digital twin. So we have once, of course, the discussion: do we always need a level 4 digital twin? Is that really needed? Most probably the answer, or our answer, is no.
Not always.
Not always. And then, of course, the second question is like the fidelity and how good does our model need to be? Because, and I think we don't have a one-size-fits-all within Siemens Energy, because what I focused today very much on was this whole question around how can digital twin help our service business, so help ourselves, making basically predictions and improve our own service performance. That's of course where most probably I want to have a bit of higher fidelity, because really then also we maybe don't send field service guys out that make checks, compared to when I maybe want to have a bit of broader software offering, what we are also planning to have, right? So when you look into the whole software as a service environment, for some customers that even don't have a service contract signed, that don't have operators on site that frequently check, for them it might be enough if we have a lower fidelity level, simply because just the pure knowledge of something could be wrong is better than before. And I think that's also where we say, okay, depending on the use case, we have different fidelity levels. So I know it's not a answer to the spot what you do, but I think it really depends also on the use case that we in the end have behind it.
I guess we have time for one last question. Yeah, sure.
What are the limitations for digital twins? Because moving forward, there are no limitations, right? But there's certain, for manufacturing, there's certain equipment, right? How do you get the data out if it's not smart? How do you connect to it?
So the question is really around how do you sort of look at brownfield installations where you have existing equipment that's not, say, smart, and how do you connect to it? Really, really good question. I can tackle that from an AWS perspective, but maybe there's Siemens Energy has a
Feel free to start, and then I jump in.
So with that, there are a lot of companies out there, and we have partners out there that are developing, say, retrofit sensors, for example, that you can add to the equipment in order to be able to then take certain key measurements. For example, it could be vibration measurements, or it could be temperature measurements and pressure measurements, for example, and then that gets connected to a backbone, either through 5G, local 5G network, or through just Ethernet cables. But ultimately, you do need to have some kind of a sensor that is gathering data of some kind. We do have some appliances at AWS that we do make. For example, Monitron is a service that we provide, and you can get appliances that are certified that will actually connect and get some of that data. And then once you can collect the data, then you can now start talking about pull it into IoT Core, IoT SiteWise, and then taking advantage of the other services on top of that. But that's for, say, a particular suite of type of equipment. If you're starting to talk about industrial equipment, which might have much more sort of ruggedized needs, high temperatures, high pressures, I'll let Clarissa maybe address that, how they look at their brownfield sites.
Yeah, and I mean, what we see is we don't have so much the problem when we look at our different twins, when you think about the system reliability twin, for example, where we really look at the condition of equipment types, because that's where we have the sensors, there we have enough data at hand. The problem for us starts, as I mentioned before, if it's of course, new equipment types, because then we need to bring the data in. But the second question we have is when you think about, I mentioned the autonomous operations twin, where we basically don't only need to understand what's happening inside a machine, but when we also look at our equipment types from outside, right? So we look at leakages, we look at strange vibrations, all things that most probably, or often the standard sensors are not able to capture. And that's when we then, of course, look into deploying cameras, look into deploying audio systems. So basically, it's then a case-by-case decision. If I really want to come up with this digital twin, do I have enough sensors? Or is there anything that I can simply add to enrich my current system? And that's what we then would do. But the good thing is, I think, at least we never came to a limitation of that we don't have a sensor or a camera or something at hand that can fix the problem. So that's something that really never occurred to us so far.
Great. I think with that, we're just about out of time. Clarissa and I will be available. We'll just be standing outside. If you have any further questions, more than happy to answer them as well. But with that, I want to thank Clarissa for joining us here on stage to tell us about Siemens Energy's story and how she's worked with AWS. Thank you, Clarissa.
Thanks for having me, Adam. And thanks, everyone.